Okay, so you can see that, right? Differentiation. We're good to go? Excellent. All right. Let me shrink this over a little bit. And so I can see all your bright shining faces. That's adorbs. Okay. As I've mentioned a couple thousand times, we're moving on to our second of only 3 topics in calculus, known as differentiation. Some of you that have had physics might have done this before. You might know how to take a derivative. That's okay. Today's lesson is a lot of algebra and some theory. Okay, maybe a little bit of geometry too, but we'll get to that in a little bit. Okay, so we're going to talk about tangent line, and we're going to compare a tangent line to a secant line. By the way, for those of you that haven't noticed, I really like teaching math, but sometimes I get a little too excited and I go very fast. Do not be bashful about hitting that space bar and saying, Reedy, slow down. Okay, I can do that, especially when we get into something like this, which is somewhat interesting. Okay, so we're going to talk about the difference between tangents and secants. Okay. How does a tangent hit a graph? How does a secant hit a graph? We're going to find the slope of a tangent line, which is the gist of what we're doing today. And I got a pretty picture to explain all that for you. This you're not going to like, but we're going to talk about the limit definition as the derivative of a function. So we're going to start taking the derivative using that big scary thing we did in problem number 5. But as you practice it, you will get better at it. And then we're going to talk about differentiability versus continuity. For those of you that had me for geometry, you remembered one of the things we talked about all the time is the relationship between dogs and golden retrievers. Yes? Alex, you're shaking your head. Explain it to the group, please, so I can stop talking for a second and take a drink. Go.
Okay, well, I remember that we were talking about it, but I'm not exactly sure everything.
Oh my God. I give you control one time and you screw it up.
Is it that a golden retriever is always a dog, but a dog is not always a golden retriever?
Tessa, 4,000 extra credit points. Good job. Alex, minus 4,000 points. And then you should be able to hold your breath for 45 seconds. Give me a second here. Okay, take a deep breath. Ready? 3, 2, 1, go. No cheating, breathing through your nose. "30 seconds. Is anybody actually doing this, or am I just amusing myself? Oh, good job, JT. I'm proud of you, buddy. As long as one person's doing it, it makes me happy. 20 seconds. 15 seconds. Bella, you're cheating. 5 seconds. 4, 3, 2, 1. That's time. Good job. All right, there's your practice for today. Let's move on. Tangent line versus a secant line. What's the difference? Okay. Well, a tangent line hits a function in exactly 1 point, and only 1 point. And since there's only 1 point, it makes the calculation of a slope, which is what we're going to be doing, a little tricky, because I'm sure you all remember from Algebra 1 that you need 2 points to find the slope. We'll talk about that in a second. We're going to come... Oh, I was starting to get worried. Gabe's back, everybody. Gabe, you okay, buddy?
Yeah, my Wi-Fi cut out for a bit.
Oh, okay. You didn't just like run up to the store and get a sandwich or anything?
No, I didn't.
Okay, all right. Secant line intersects a graph in more than 1 point. Now, it could be a lot of points. Could just be 2, could be 3. If you think of the sine graph, if I was to put a horizontal line through a sine graph at, say, y equals 1/2, it would hit in an infinite number of points. We're going to see an example today where it hits in 3 points. And the gist of the lesson today is we're going to compare the tangent line to the secant line. And so we're going to go from an Algebra 1 concept to a calculus concept. Okay? So, let's see if this works. Oh, yes. Okay. So I got this pretty picture, and let's talk about what's going on here. Let me lay the groundwork for what we're going to talk about. You will see 2 points on that graph, P and Q. Are we good to go there? Okay. So P is some random point, and you'll see it has an x value of x. It doesn't matter where it is. It just happens to have a value of x. And because this is calculus, we're no longer talking about x and y. We're talking about points being x comma f of x. Okay. Where f of x is the same thing as y, but we're big people now, and so we use f of x. So notice that P has an x value of x. It has a y value of f of x. Okay, good? Now we take Q. Where is Q? Well, Q's over there somewhere. So I moved over to the right and got Q. How far did I move over to the right? You'll see at the bottom, I moved over delta x units to the right. I didn't have to go to the right. I could have gone to the left, but I decided to go to the right. And then where is Q's y value? Well, the y value would be the y value of Q's x point. So Q's x point is x plus delta x. Therefore, its y value would be f of x plus delta x. Let me stop and take a breather. Is everybody with me so far? Any problems? Now, you'll start to see that some of this stuff is going to look familiar. This f of x plus delta x, this delta x thing. Puzzle pieces starting to fit together. Okay? We're good. Beautiful. Now, please calculate the slope of the green line, the line PQ. Oh, by the way, hold on, before we go any further, notice the red line is a tangent line, hits at 1 point. The green line is a secant line, it hits, in this case, 3 points. But calculate the slope of PQ, please, if you can. I don't mean to insult anybody, but remember that slope is y2 minus y1 over x2 minus x1. For those of you that have the answer, that should look fairly familiar. How many people have the answer? Give me the emoji thumbs up, please, if you have it. Good, good. We're getting there. Ooh, hey, there's new emojis. There's a heart. There's a joy. Did anybody else know this? Hannah's just shaking her head like this guy's a moron. Thanks, Hannah. Appreciate the vote of confidence. I get excited about one thing and you shut me down.
Hey, I didn't say anything.
Yeah, whatever. Okay, slope of PQ, f of x plus delta x minus f of x over x plus delta x minus x. That's y2 minus y1 over x2 minus x1. You may have done it backwards. That's okay. Well, look at this on the bottom. Whoosh, whoosh. Oh, yeah. So that gives us the slope being f of x, plus delta x minus f of x all over delta x. And that should look familiar. That's the slope of the secant line. But we don't want the secant line. We're calculus. We want the tangent line, which we're going to get to eventually. All right, are you with me? Everybody's good? Some simple algebra practice there? Hot diggity. Okay, so here's my picture again. And again, Q is the secant line. We want to find the slope of the red line, but by looking at that picture, you can see I can't do that because I don't have 2 points. I only have the 1 point P. I need something else. Okay? blah, blah. Yeah, we did this already. Okay, great. There it is. Excellent. Okay, moving on. What happens when you move Q closer to P? What's going to change?
The slope?
Good.
Delta X.
Okay, the slope, yes. Delta X, yes. Anything else?
The y value as well.
Good. Okay, so let's go back here. Start this again. Nope, bad. Here. Okay, yeah. Okay, watch this. By the way, this takes a lot longer than I thought it would, so we'll just watch this happen. So. Yeah, look, delta X is changing. The Y value is changing. Slope's changing. Let's stop right there. What's going to happen eventually?
We get really close to point P.
How close?
Exactly at point P?
Okay, so what's going to happen when Q goes to P?
It'll be equal.
Good. What's going to happen to delta X when Q gets very close to P?
Be 0.
Excellent. What do we call that in calculus? When something like delta X gets very close to another number.
A limit.
Yeah. Bingo. So, let's get rid of this. And no, I don't care. And go back to this. Okay. Did that already. So notice the point Q slides closer to P, and it doesn't matter about the shape of the curve. As it gets closer and closer to P, delta X gets closer and closer to 0. Theoretically, it will eventually go to 0, but we don't care because we're talking about limits. Remember, limits are not the value, it's as it gets very close. And so we get that puppy. And that's in a rectangle, so it must be important. The slope of the tangent line is that limit equation we've started using already. The limit as delta X approaches 0 of that business. Now, something that's going to come up in discussion is going to be the difference between this and not having the limit on it. So if I get rid of this limit statement, okay, that versus this. And it's really simple. If it doesn't have the limit statement, it's the slope of the secant line when Q was away from P. When it has the limit, then it's the slope of the tangent line when Q and P are the same point. Now, this is a pain in the butt, as illustrated on problem 5 from that intro worksheet. We're going to do this a little bit, get some practice at it, and then over the next couple weeks, I have only one goal, and that is to teach you different ways to find the same solution. And it will sometimes get easier, it will sometimes get more difficult. We'll cross that bridge when we get to it. Oops. Okay, so let's do an example. Here's a nice quadratic. It opens up because the A term is positive. It's got a vertex somewhere. I don't care about it. But I would like to know the slope of the tangent line, which is, just for refresher if you're lost, it's this thing. So what I'm asking you to do in part A is apply this formula to that function. Go. If you think you have it, please give me the whatever that thing is. The celebration emoji. All right, good, good. Couple people, excellent, excellent. Getting there, slowly but surely. Don't call me Shirley. Ooh. Noah, where'd you get the question mark?
Me?
Yeah.
I didn't do a question mark.
A question mark just popped up on your screen.
I did the thumbs up.
Do it again. Nope, yours is a question mark. Do a different one. Does everybody else see the question mark, or is it just me? You all see the question mark. Okay. Do the I don't know. Do something else.
I'm gonna clap hands.
Okay. Question mark.
What?
Question mark. Oh, I'm sorry. That was shocked. What? Not you couldn't hear me. Yeah.
No, yeah.
Oh, sorry. My bad.
That explains a lot. Okay. I don't know how to fix it.
Guess you can't do remote learning anymore.
Well, maybe I'll. What does this do?
That raises your hand.
Okay, well that's right. Can I change it? Is that possible?
I don't know.
Okay, I'll figure it out on my own. Thank you, though.
I'm here for you, buddy. Maybe you have to update Zoom, or
I didn't
drop,
know if it was possible.
or drop the class. I don't know. Okay, let's move on. So something happens here that's a little bizarre, and we'll get to that. So plug and chug. You get that, and then you square your binomial. Remember that x plus delta x squared is not x squared plus delta x squared. You got a b term there, so you get that mess. And you see that I distributed the minus sign over there because you got to be careful with that. And then I got that big long mess there, which I'm sure some of you got. And then I started canceling things because there's an x, a 2x, a 3x squared, and a negative 3x squared. And then I noticed that all those other terms had a delta x in it, so I factored out a delta x. And then I crossed that stuff out, and I got down to that. Why is that bizarre?
Because there's still a delta x.
No, I got rid of the delta x. I got 6x. Here's my final answer. That's why I took the limits of the delta x from 1.
Delta x.
What's that, Jack? I'm sorry. Nobody's bothered by that answer?
What to do with the plus 3 delta x?
Say that again, Gavin. I'm sorry.
Oh, never mind. I got it.
Yeah, I took the limit, so the delta x thing disappears.
Mr. Reedus, does that have to do with something that, like, it's a formula for a line?
Yeah. Notice we're taking a slope here. And pretty much up until this point, every time you've taken a slope, you've gotten 2 answers. Either a numerical answer or does not exist for a vertical line. You know, or, you know, the no such thing. No slope. Now all of a sudden we're getting a formula for a slope. How is that possible? Or what does it mean? Okay, so if we go back to the picture, multiple clickings. Oh, there we go. Okay. So what we're doing is we're calculating the slope to this function. Now this isn't the function, but I can use this to illustrate it. At some random point, and we don't know where the random point is. If, for instance, I choose the point to be over here, then my slope would look something like this. However, if I picked a point over here, my slope would look something like this. So the actual value of the slope changes depending on where you are on the function itself. Okay. And that's a fairly new concept. I don't think you would have seen that anywhere before. Because when we do this calculation, let me get caught up here. When we do that calculation, we're getting an equation for the slope. Because the value of the slope can change depending on where you're at. Well, where are we talking about? This particular problem, I think it said 4, 40. So I would plug 4 in for x and get 22. So at this particular point of 4, 40, the slope is going to be pretty steep and positive of 22. If I put in a different point, let's say x equals 0, I would get a slope of -2. And you can put in an infinite number of points there and realize that the slope changes. If you think about that being a parabola that faces up, you know, if you take the slope over here, you'll get this. As you come around, you get the vertex and then back up. That slope is constantly changing. And initially, that's a hard concept for some people. It's bothersome because you want to get a numerical value. And it's not. It's an equation. Then part B says, well, what's the slope of the tangent line? 2 things for the equation of a line, a point and a slope. Here's my point, 440. Here's my slope, 22. Put that together into that equation. If you change the point, then you change the point and you change the slope. Questions about that so far? Or does it make sense? Some of you look like your brain's going to melt. That's okay. It'll sink in eventually. There's the fancy schmancy stuff in the blue box. It's what we already talked about. So this delta y over delta x, you know, is a slope. But for calculus sakes, they're going to do that. And notice they replace the x's with c's because we're talking about that one particular point. Before we had the general formula in the purple rectangle. Here's the general term in terms of a point C. Okay. For our discussion, if we go back to this, C in this case would be 4. And that'll change from problem to problem. Okay, now, what happens if you've got a function that has some weirdness to it? So, for instance, if you think about, before I talk about this, if you think about that parabola we just looked at, it faces up and it has a vertex. And we happen to look at a point over here that had a big steep slope of 22. What's the slope of the tangent line at the vertex?
Is it a horizontal line?
Good. Which would have a slope of?
0.
0. If we go back to that previous problem and we figure out where the vertex is using negative b over 2a like we talked about before, and we plug into that slope formula, we should get a value of 0. But it will change depending on where on the graph you're talking about. However, some strange things happen. So before I do this, let me go to the picture and talk about this. Okay, so notice what's happening here. I've got some curve. And as the curve moves to the right, it's got this point called C where all of a sudden the tangent line is vertical. Okay, so you start here, it's got a tangent line that looks like this, and then the tangent line looks like this, and then it gets there, and then eventually it's going to be there with a vertical tangent line. What's the slope of a vertical line? Undefined. But then as we go past that point, we can start to get slopes again. So it's only at that one particular point that it has an undefined slope. Well, how are we going to know where that happens? For calculus, we've got a nice, easy way to do that. If you think about those slopes I drew, I went from a nice level slope, little increase, little more increase, a lot of increase, and eventually it gets to a point where you have one of these two scenarios. If the slope of the tangent line is infinity or negative infinity, then you have a vertical tangent line. So up until this point, you always talked about a vertical line having no slope. But now with calculus and limits, we can say it has a slope of infinity or a slope of negative infinity. We're going to use these two things to check to see if it has a vertical tangent line. It doesn't happen very often, but it does happen occasionally. Because we've seen plenty of limit problems where when you take the limit, you get a value of infinity or negative infinity. Most of the time, we're going to get nice, pretty things. Simple equation, plug in the point, good to go like the previous equation. Okay, so this whole business that we did is what's called taking a derivative. Finding the slope of the tangent line is the derivative of a function. And so we have some new notation now, you'll see. That's read as f prime of x. If you're talking about the function g, it would be g prime of x. If we do this twice, you get f double prime of x, but it's defined as that limit equation. The noun is a derivative, the verb is differentiation. Now, there are a whole bunch of different notations for this. I'll explain why in a little bit. We're going to have a little history lesson here, and I'll tell you why there's different notation. We use the first three most commonly. F prime of x. The second one means the derivative of y with respect to x. The third one is y prime, obviously. So if you have a function y, its derivative would be y prime. And then the other two are just variations of what we'd already talked about. The derivative of f of x with respect to x, and then the derivative of y with respect to x. The first two are our most common that we'll see. And starting out, almost everything is going to be in terms of x. There are scenarios where that will change, but those are way down the road. Nothing you need to worry about now. Okay, how we doing? Good. Let me see my next slide. I think. Okay. Yeah. Let's take a 5-minute break. Okay? I'm going to start a timer for 5 minutes. Feel free to hold your breath for that, but go and find something to do for 5 minutes. We'll come back and start with a little history lesson. Okay? Go. All right, that's time. Let's go. Okay, so as I was saying, we've got different notations. And the two main differences are the f prime notation and the dy dx notation. And the reason we have two different notations is because of these two knuckleheads. Isaac Newton. Who's heard of Isaac Newton? Raise your hand. Yep, hit on the head with an apple, physics. And, of course, your friend and mine, Gottfried Leibniz. Who's heard of him? No, nobody? Before we get started, I would like to point out, check out the hair on that dude. I mean, I'm jealous. The flowing locks, the whole business. Okay, so Isaac Newton, Gottfried Leibniz, both mathematicians. Isaac Newton, you've heard of him before. Physics things, math things. Back in their day, mathematicians were like rock stars. Everybody knew them. They signed autographs on the streets. Never paid for anything. No, we've got that, Mr. Newton. You did the Apple thing. For some bizarre reason, these two knuckleheads come up with Oh, sorry, I forgot something.
Ladies and gentlemen, let's get ready for rumble!
So I spent the time to put it in there. I might as well use it. So they both come up with calculus at about the same time. And the concepts were the same. The notation is different. So Newton, I believe Newton is the f prime of x notation. Leibniz is the dy dx notation. But they came up with the same concepts. Well, word starts to get out. When you start to create an entire branch of mathematics, you involve people in the process and they check on it. And some people go to Newton and they say, hey, this dude Leibniz is doing the same thing you're doing. And Newton couldn't do this. He could not have this. He had an ego like you wouldn't believe. Leibniz was a pretty quiet, reserved guy, not nearly the rock star that Newton was. So Newton finds out that Leibniz is doing the same thing, accuses him of cheating or plagiarism. There's no proof of that. So he basically spends the rest of his days ruining Leibniz. So Newton, everybody knows Newton, famous. He's in all the history books. Nobody's ever heard of Leibniz because he pretty much died broke and poor at home after creating calculus. I know it's a sad story. I didn't mean to bum anybody out today, but that explains why we have two different notations. Okay. The other notations, those just popped up along the way. Okay. All right, so let's do an example. I'd like to find the derivative of f of x. Okay, so what's going to become common here is the terminology. Taking a derivative. Well, what does the derivative represent? It represents the slope of the tangent line at a certain point. And in this case, we don't know the point, so we're just going to come up with a general formula for that thing. Okay, so the slope is equal to the limit as delta x approaches 0. You have to have the limit because without the limit, it's just a secant line. X plus delta x, quantity cubed. Oh, that's going to be fun. Plus 2 times the quantity x plus delta x. Okay, that's my f of x plus delta x minus brackets x cubed plus 2x all over delta x. Okay, that's step 1. Sam, how would you do x plus delta x cubed? Any ideas?
I know it's like a plus b and then like.
That's factoring. Here we're multiplying it out. So if we were going the other way, if we were breaking it down, we'd do that. But this is something different. How would you multiply it out? Would you just...
Oh,
Go ahead.
going to be x third and then change of x would be to the third. But then I'm not sure like the middle would be.
That's the key. Okay, so what I'm fishing for is whether or not anybody knows a different way than just multiplying this puppy out, x plus delta x times x plus delta x plus x times delta x. Does anybody have another approach? No?
Binomial expansion.
Oh, ooh, Sarah, using big words. What did you say?
I said binomial expansion.
Binomial expansion. can see that. Do you know who created that binomial expansion? Do you know that other mathematician's name? Anybody? Rhymes with Smaskel.
Pascal.
Pascal's triangle, very good. So if you remember Pascal's triangle, you could use that. I never remember it, never learned. I did learn it, I just forgot it. So I'm going to do it the old-fashioned way. And I'll probably screw up along the line, along the way, because I'm under pressure here. And I'm going to run out of room. Maybe not. X cubed plus 2x squared delta x plus x times delta x squared plus x squared times delta x plus 2x delta x squared plus delta x cubed plus 2x plus 2 delta x minus x cubed minus 2x. Oh, I'm exhausted. Uh-huh. Whoosh. 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 Whoa. Uh-huh. So, what have I got? I got a limit as delta x approaches 0 of one of those, and another one of those is 3 of those. Okay, that takes care of that and that. And then I got one of those and 2 of those. That takes care of that, plus 3x delta x squared plus a 2 delta x, sorry, plus a delta x cubed. Oh my goodness. Now, the reason I chose this problem was not to show off with my vast stores of mathematical skills, because I'm pretty sure I'm going to screw up somewhere along the way. The reason I chose this problem is to show you and try to convince you that this sucks. So we're going to come up with better ways to do this. But until we come up with a better way, we still got to grind this out. Lexi, I don't mean to put pressure on you, but could you confirm for them that there is a better way to do this?
There is a much faster way to do this.
Thank you. Whew. Okay. Now I got down to that. After that mess, I've got that thingamajobber, and then the last thing I'm going to do is take the limit. So you'll recall, because we've been doing it for a couple weeks now, when you take the limit, that goes away, and sure enough, after all that work, I get that. Lexi, is that right?
Yes.
Heck yeah, it is. I'm exhausted. Okay. Well, that's kind of weird. I took the derivative of a cubic function and I got a quadratic. In the previous problem, I took the derivative of a quadratic and got a linear term. Maybe there's a pattern there. Questions about that? I won't erase it. I'll leave it there. If I need to come back to it, I will. So you can get that copied down. But there it is. Now, suppose I wanted to go further. Suppose I wanted to know the slope of the tangent line at a certain point. Let's say 0. Well, then I plug 0 into the formula. I'd get 2. Let's suppose I want to know it at 10. I plug in 10, I get 302. Okay. After you've done all the hard work, the slope, the numerical value of the slope becomes very simple. You just need to know what x value you want to talk about. We're having fun, aren't we? Almost done. Let's talk about golden retrievers. So as Tessa mentioned earlier, we're going to use a comparison between golden retrievers and dogs. All golden retrievers are dogs, but not all dogs are golden retrievers. Why do we care with this? Because there's a relationship between continuity and differentiability. Okay, we have something called a reversible statement. And a reversible statement is a statement that's true going forward and true going backwards. So if, for instance, I was to say, since I have a wife, I am married. Is that a true statement? Yes. Okay. If you have a wife, then yes, by definition, a wife is a person you're married to, so that's true. Is the reverse true? If I'm married, I have a wife. No. Could be married to a man. Could have a husband. Okay. So the reversibility doesn't work. The same is true with this. So let's talk about this. We've got a nice little absolute value function. It's that v that you know so well. And we talk about the slope of a tangent line. So if I pick a certain point on this curve, I will get a slope. Anywhere to the left of 2, I'm going to get a slope of -1. Anywhere to the right of 2, I get a slope of 1. This, however, creates a problem. Because what does a tangent line look like there? Well, you might argue, well, wouldn't a tangent line just look like this? And the answer would be yes, that's one possibility. But what if I did this? That also only hits in one point. And this. And this. And there are a whole bunch of different possibilities. Because there are a whole bunch of different possibilities, that thing is called a point of non-differentiability. That's a big word, so we're just going to change it to a corner. The corner on a graph is not differentiable. However, notice this function is continuous. So just because a function is continuous doesn't make it differentiable. However, the opposite is true. If it's differentiable, it must be continuous. I have that summed up on the next slide. Okay? Bing, bing, bing. Okay. If you can take the derivative, it has to be continuous. But just because it's continuous doesn't mean it has to be able to take a derivative. And you're going to get those two confused. Hopefully, if you get them confused, you'll come back to that picture. Because again, this picture is continuous, but not differentiable. Okay. How are we doing? Good. So we're going to you're going to kind of have to pay some dues, meaning you're going to have to do some of these limit calculations just so you get comfortable with it. And because somewhere along the line somebody's going to say use the limit process to find the derivative. But again, over the next couple weeks / months / 2 months, I'm going to show you some other ways to do this thing to save yourself a lot of hassles.